Let's see, what else am I doing? Back. One moment. It's together here. Cool. Yeah, we're talking. All right. Okay, what Babson labeled this section, it's like something with curves and lines or something. I don't know. It's parametric. We're doing parameterization, but it's like the calculus of parameterization, meaning after we parameterize a function, meaning writing x and y in terms of a parameter t, or theta, but usually t. Then we're gonna like do some calculus, meaning we're gonna find a derivative or an integral or an arc length or right, all the things, all like the kind of physical attributes things we've done with integrals so far. We're gonna now kind of revisit them in terms of a parameterization, which is kind of funky, but not too terrible once you see what's going on. Yeah. Yes. So parametric equations. Parametric. And one of the things we often like to do is to be able to go between parametric equations and, oh my gosh, the other type, which is regular equation, rectangular, right? Using rectangular coordinates or parametric, like we have just y in terms of x or something else. And I don't really want to do that example. That one's kind of funky. So let's look at this example. So we're going to be given the parameterization x, or I like to write x of t equals t plus 2, and y of t is equal to t squared. And typically, when you're given a parameterization, you're also given some sort of domain, because we often want this thing only on a limited interval. So here we're going to say t is between -2 and +3. And we're going to graph it. So actually, we're just going to graph it, meaning we're going to just plot some points. So this shouldn't be too bad. We're starting at t equals -2, and I'll just use the nice integer values, even though it's defined to be whatever it is for any value of t between -2 and 3, not just integers. But we know that x is t plus 2, so this is going to be 0, 1, 2, 3, 4, and 5. And y is t squared, so it's going to be 4, 1, 0, 1, 4, 9. So when we graph this, we're going to get the point 0, comma 4. And then 1, 1, and then 2, 0, and then 3, 1, and 4, 4, and then 5, 9. Bless you. So it looks like this. It looks a lot like what kind of curve? Right, it looks like a lot like a parabola. And since we are doing a parameterization, we also usually try to indicate the direction of travel as t increases. So over here is when t is equal to 0, t is equal to 1, sorry, t is equal to -2, apologies. -1, t is equal to 0, 1, 2, 3. So we would draw arrows in the direction where t is increasing, like that. Now, a lot of the time when you're trying to graph these things, it's a real pain to do it this way. Like this is tedious, and this one wasn't too bad, but like it could be a lot worse. And also, we were kind of lucky in that it was a shape that was really easy to recognize. But often, when you're asked to graph a parameterized set of equations, we usually try to eliminate the parameter and see if we can just get the usual Cartesian equation using just x's and y's. So typically, if we're trying to do that, if we want to eliminate the parameter, we usually do that by isolating t in one of the two oh my gosh, I've said this word like 1,000 times, in one of the two parameterizations. So I would pick the easier one. That's definitely going to be the x one because I don't want to start square rooting things unless I have to. So I would take x equal to t plus 2 and isolate t and get t equal to x minus 2. And then I can plug that in for the t and y and get y equal to x. Oh, sorry. I said t equal to x minus 2. I wrote x minus t. Apologies. It's easy to confuse the 2's and the t's. And then y is going to equal, instead of being t squared, it's going to be x minus 2 squared, which is exactly what that parabola looks like. It's the usual parabola shifted 2 to the right. So the vertex has moved from 0, 0 to 2, 0. But there's one more thing. We still have to give the domain here. So here, since t was between -2 and 3, well, since t is equal to x minus 2, we can say that -2 is between, or I should say x minus 2 is between -2 and 3. And if we add 2 to everything, x is between 0 and 5. Not surprisingly from our graph, right? We started at an x value of 0 and ended at an x value of 5. So nothing too crazy happening here. Questions so far before we do a few more things? I see faces of consternation, but no questions, just like kind of what are we doing? What we're doing is we're trying to look at some parameterization, just kind of get a feel for what's going on and try to see like what does this stuff really mean? What are we doing with it? What can we do with it? So really at this point, we're just saying if you have a parameterization, how would we graph it? And one way certainly to do this is to plot points, but often we prefer to try to make it look like something we're used to seeing. Make it look like an equation that doesn't have our parameter t in it. So that's what we're going to do with the next couple ones. So the next few are going to be not super exciting. Yeah, let's do that one first. Sure. So let's say this new parameterization is, this is number 2, x equal to e to the 2t and y equal to e to the t. And t is greater than 0. So I don't really want to, but I could solve for t in one of these. If I had to pick one of these to solve for t in, I'd probably pick the second one here because it's just less complicated slightly. Although you really don't have to do that. Like I could say, yeah, t equals the natural log of y, and then plug that back in over here and get x equal to e to the 2 natural log of y, which is then e to the natural log of y squared, which is then y squared. But it might have been a whole lot easier to have just observed that x being equal to e to the 2t is e to the t squared. And then y is equal to e to the t, so that's going to give me x equals y squared. And before I get too crazy, well, no, actually, I'm just going to draw it even though I know I'm kind of making a mistake. I'm just going to draw x equal to y squared, which is my usual rightward opening parabola. Atypically, I'm not going to draw any arrows. Usually I would say that like this thing keeps going to the right, keeps going to the left. But really, I just want to draw the actual part of it that I want. So if I focus in on the fact that t needs to be greater than or equal to 0, well, that means the smallest x can be is e to the 0, which is 1, and the smallest y can be is e to the 0, which is 1. In fact, x and y, or I should say specifically, y here should never be negative. Y can't, well, not should never be, isn't, right? If y is e to the t, y is never negative. So for sure, x is bigger than or equal to 1, y is bigger than or equal to 1. So we're starting over here at 1, 1 when t is equal to 0, and then we're moving that way. So really, we only should have graphed that part of it. We should have just graphed starting at 1, 1, and then going that way. So as is often the case with parameterizations, you often don't get the entirety of the usual Cartesian graph. It's kind of funky. And I'll point out, if you had said, well, James, that's just because you limited what t could be. Kind of. If we had instead said, okay, well, let's say that we have the same parameterization, x equals e to the 2t and y equals e to the t, and now t can be any real number. Well, what's e to the negative infinity? Or what does e to the x get really close to as x gets really, really negative? Think about the graph of e to the x. If you go that way, we're getting closer and closer to the y values. We're getting closer and closer to the horizontal asymptote of y equal to 0. Right? Here's your graph of e to the x, or I guess e to the t. If t goes way that way, oh yeah, my function values get closer and closer and closer to 0. So what that means is, if we start over here at t going to negative infinity, over here, x and y are both getting closer and closer to 0. We're not actually ever getting there. So this graph is going to look like this. We're starting almost at 0, 0. And then it's just the right half of that parabola, or the top half of that parabola. So right here at 1, 1, that's where t is equal to 0. And over here at, say, 4, comma 2, that's where t is equal to the natural log of 2. And over here, right, when we go from, if we go back this way, this is where t is going towards negative infinity, and x and y are both approaching 0. Kind of weird. Parameterizations are kind of weird. Let me give you one more weird one.
So is the answer to the question?
Yeah, so you make an excellent point. I didn't ask a good question, or I didn't really ask a question at all. I should have said something like graph the parameterization. Parameterization by eliminating t. Because that's what we're really doing. We're trying to graph these things by making it quote unquote easier to graph by eliminating the parameter so it looks more like an equation we're used to seeing, right? We're used to x equals y squared or y equals x squared. Let's look at this next one. Yeah, this next one's also kind of weird. So let's say we have the following parameterization. X equal to cosine of t, y equal to cosine cubed of t. And we're going to say that t goes from 0 to 4 pi. 4 pi? Sure, that's annoying. All right, I want you all to try to find the Cartesian relationship. So find y as a function of x. Should be pretty similar to how the last one worked. Or I forget. Here's the equations. So I'm getting y equal to x cubed because x is cosine and y is the cube of cosine. So I'm going to be careful though, because I'm definitely not going to get the entirety of the cubic function. Right? I'm definitely not getting all of this. Why not, you say? Well, because what's the largest value cosine can ever have? 1. What's the smallest value it can ever have? Right. So we're limited, right? X can only be as big as 1 and small as -1. So really, we're just getting this portion of the cubic graph from starting at 1, comma 1 when t is equal to 0. And now this one's extra weird because it's going to go back and forth. It's going to go from 1, 1 at t equals 0, and then it's going to go down to 0, 0 at t equal to pi over 2. And then it's going to go over here down to -1, -1 when t is equal to pi. And then it's going to reverse course. It's going to go this way, and then it's going to go back the other way, and then back the other way, back the other way, back the other way, back the other way. It's going to do that like, I think, 4 times, right? 0 to pi, pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi. So we end up where we started. Okay. Again, just different, right? Not what we're typically used to seeing. But again, most of these graphs are still going to look pretty familiar. They just might be kind of truncated. And I don't think Alex can really talk about this next part, but this next part actually is kind of super important for when you take 21C. Yeah, 21C? Yeah, I think 21C. Kind of being able to go the other direction, trying to take some Cartesian function curve and parameterize it. I'm thinking specifically about lines in 3 dimensions. Which you change it, right, where it's not just y equals some mx plus b, it's really like y equal to some point plus some vector times your x, essentially. But we can very, very easily parameterize lines in 3-dimensional space or 2-dimensional space. For example, we want to parameterize, and for a word so close to my last name, you think I'd be better at saying it, parameterize each curve. So the first one's going to be the line segment starting at 4, comma -1 and ending at, let's say 1, comma 7. So there's a lot of ways of doing this. I'll give you kind of the standard way. So we're starting at 4, -1, and we're ending at 1, comma 7. So here's what I'm going to say. I know that x of t, the x coordinate, is going to start at where? 4 or 1? Should be 4. And y, so I'm not done with that, but I'm leaving, and then I know that y of t is going to start at -1. And then the easiest way to do this is to say, this is going to be what we have when t equals 0. And then you're going to add some multiple of t. And the multiple of t is how much change you have in that particular coordinate. So x is going to decrease by 3. So I'm going to say, essentially, 1 minus 4 times t. Similarly for y is going to increase by 8. So it's going to be I know I said 8, but I'm writing 7 minus minus 1 times t. And then you make the smart choice of saying t gets to go from 0 to 1. Let's check it out. If x of t is 4 minus 3t and y of t is negative 1 plus 8t, when I plug in t equals 0, I get x comma y equal to, not surprisingly, 4 comma negative 1. When I plug in t equal to 1, I get x comma y equal to 4 minus 3 for x and negative 1 plus 8 for y. And that's pretty typical of how people do this. You're trying to parameterize the equation of a line that goes through 2 points. You pick a starting point, that's when t equals 0. You pick an ending point, that's when t equals 1. And then the thing you're multiplying t by is how much each of the variables or each of the functions that are parameterized change by. So we're going from there to there, and we're going that way. Is this the only way to do it? Definitely not. I could have said negative 1 plus, sorry, I could have said 4 minus 3 over 2t and negative 1 plus 4t and said t goes from 0 to 2. I could scale the multiple of t by anything I want and then increase the domain of t by that factor. But this is the pretty standard way of doing it. And let's point out, if we wanted the entire line, that went through those 2 points, through the points 4 comma negative 1 and 1 comma 7, we would just say that our parameterization is x of t equal to 4 minus 3t, y of t equal to negative 1 plus 8t, and t is going from negative infinity to infinity. Only difference. That would give you the entire line. So hopefully you all could imagine that I could do exactly the same thing for points in 3 dimensions. I would just have to have a third parameterized function, a z of t. So just as a quick kind of aside here, if I wanted to say, get the line segment between, I don't know, 3, negative 2, comma 1, and 1, comma 8, comma 5, I would say, well, I should say from this point to this point, I would say that x of t is 3 plus how much times t? What do I want to multiply t by in this case? If I'm trying to get from 3 to 1. Almost. I mean, you could do 2, but I'm gonna make it negative 2 because I'm gonna let t start at 0. That's gonna give me x equals 3, and then t is gonna end at 1. That's gonna give me 3 plus negative 2, which is positive 1. And then y of t in a similar way will be this starting point plus the difference here, which is 8 minus minus 2 times t, and then z of t would be 1 plus 5 minus 1 is 4t. And that would give me the equation of the segment. And if I wanted the entire line, I would do the same thing. I would let t go from negative infinity to infinity. So that's a really, really easy way of parameterizing any line between 2 points in 3-dimensional space. And that is something I'm pretty sure you do in 21C, or at least have use of in 21C. We're not just doing it because it's really bizarre. It also has purpose for another math. Like the purpose is to use it in another math class, but still, like, okay, that's something. Sure, yeah, let's do that. So a couple more, and then we'll get to the calculus parts. So let's say we want to parameterize the part of y equal to x squared minus 2x minus 8 that is below the x-axis. Okay, well, there's a really easy way to parameterize things. You let x be t and you let y be the function with t's in it. That's almost always going to work. So one way to do this is to say, yeah, our parameterization is x of t equals t and y of t equals t squared minus 2t minus 8. Then the problem here is we have to figure out what our bounds for t are. because we want the part of the parabola below the x-axis. So it's, I don't know, this parabola looks something like, I don't really know what it looks like actually. It looks something like this. That's not the best parabola I've ever drawn, but you get the idea. So we want to find out what the x-intercepts are to find out what the bounds for t are. So set this whole thing equal to 0, x squared minus 2x minus 8 equals 0. I think that factors as x minus 4 times x plus 2. So we need x or t to go from -2 to +4. Okay, but those are all kind of strange examples, I would say. They're maybe atypical, although they can come up sometimes. Sometimes people ask weird things. Let's talk about the more typical things, like say we want to parameterize, I can spell, the which half? Sure, the left half of the circle, x squared plus y squared equal to 9, starting at the top, 0, 3, and moving in a counterclockwise direction. It would have to be counterclockwise if you're starting at the top and going on the left side of the circle down to the bottom. So we're starting up here at 0, 3, and we're tracing out the left half of the circle until we get down to the point 0, -3. So for circles, you typically want to let x and y be cosine and sine, respectively. Well, actually, I should say you can kind of actually pick whatever you want. So usually there's probably at least two relatively easily accessible ways of doing this for any kind of circle, depending on your starting point and your direction of travel. So typically, although you don't have to, for counterclockwise direction, you usually let x equal r times your cosine. So in this case, x is going to equal 3 times cosine of t, and y is going to equal 3 times sine of t. Because if you think about back to like trigonometry with the unit circle, we think about our angle increasing in a counterclockwise direction. So if we want to go around the counterclockwise direction, we let cosine be the x coordinate and sine be the y coordinate. So then the only problem here is we have to figure out the right starting place. So I want to start at when cosine is 0 and sine is 1. So I want to start at t being bigger than or equal to pi over 2. Because cosine of pi over 2 is 0 and sine of pi over 2 is 1. And then we're going to go all the way down to here where our angle is 3 pi over 2. The reason this works, by the way, is because these parameterizations satisfy this equation, right? If you plug in x equal to 3 cosine theta, or t, sorry, you get 3 cosine of t squared, and y is going to be 3 sine of t squared. And if you multiply this out, you get 9 cosine squared t plus 9 sine squared t, which is just 9 times cosine squared t plus sine squared t, but that's 1. So you get 9 times 1, which is 9. So almost always when you have x equal to cosine and y equal to sine, or you have a circle, you know that those two things are related to each other. That's almost always how we think of it. Back to this though, I'll just point out, this is not the only way of parameterizing this. I could have alternatively said, I'm going to let x equal 3 times sine of t. Yeah, that'll work. I'm trying to make sure this works. Ooh, yeah. I'm already regretting my choices here. Yeah, is that going to work? I don't know. We'll figure it out. Y equal to 3 cosine of t. Now, if I start at t equals 0, what do I get? I get 0, 3. But then if so, t equals 0, I get the point 0, 3. Looking good so far. If I go to pi over 2, sine pi over 2 is 1. Cosine pi over 2 is 0. So I think I need a negative there to make that work. And then t equals pi, I get -3 sine of pi, which is going to be 0. And 3 cosine of pi is -3. Yeah, that totally works as well. So here's another different way you could parameterize this. So almost always, especially with circles, you always have options. And it doesn't really matter what you choose because as long as it's correct. So I typically, for circles, make sure that I look at the starting place and then I look at like a quarter of a circle later and make sure I'm going in the right direction. So that's why I plugged in t equals 0 here and got, oh yeah, 0, 3, cool. And then I plugged in pi over 2 and accidentally got 3 comma 0, but knew I wanted negative 3 comma 0. So I changed the x parameterization to be negative 3 times sine so that I end up getting the right kind of things. Okay. There was one example Babson did that I thought was kind of interesting. So he did one where he kind of went the other direction and said something like, what if you're given, sure, something like x equal to, he did something like this. I think it was like x equal to cosine of t and y equal to, I don't know, let's make it annoying, 5 sine of t. And then tried to find a Cartesian equation for this. I think he did that, something like that. Maybe he went the other way. Sorry. No, he did this. So when you see something like this, if you're trying to make it to a Cartesian equation, you should be thinking circles. I'm thinking circles. I just don't know exactly what. So I know what I want to get. I know eventually I want cosine squared plus sine squared. I need that, and I need them to have the same coefficients. So the problem here is that if I just square both of these, I'm gonna be off. So it looks like for them to have the same coefficients, I need to multiply x by 5. So I'm gonna say 5x is equal to 5 times cosine of t. And then if I square this and square this, 5x squared plus y squared, well, that's going to equal 5 cosine squared plus 5 sine squared. But that's just going to equal 25 because what's happening here is I'm getting 25 times cosine squared plus 25 times sine squared. And I factor out the 25, I just get 25. So this parameterization leads to the Cartesian equation 5x quantity squared plus y squared equals 25. Or you could write it like this. Or another way of writing this, which is fairly standard, is to divide everything so you have a 1 on the right-hand side and write it as x squared plus y squared over 25 equals 1. All these are the same. What's the graph look like? It's almost a circle. Well, let's plot some points. Let's see. Let's go back to the parameterization. If I start with start with t equal to 0, cosine of 0 is 1, sine of 0 is 0. So I get the point 1 comma 0. And then if I plug in t equal to pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. I get 5 times 1, so I get 5, 0 comma 5. And then at pi, I'm over here at negative 1, 0. And at 3 pi over 2, I'm down here at 0, negative 5. So I actually, instead of getting a circle, I get an ellipse. Which is also the same graph you get if you thought about graphing this. Right? If x is 0, y could be plus or minus 5. And if y is 0, x can be plus or minus 1. So same equation. All right, let's get to the fun part. Hey, wasn't that the fun part? No. This is so fun, right? The parametric. Oh gosh, I kill myself over here. The parametric stuff is always feels kind of weird, but let's look at some of the calculus stuff. So we're going to use this next example for quite a bit. Where'd you go, pen? Cool. So we're going to consider the parametrically defined curve x equal to t squared and y equal to t cubed minus 3 times t. And t can be any real number. T is between negative infinity and infinity. So unlike our previous examples, it is not particularly nice to eliminate the variable t here. We could, but there's a whole plus or minus thing, and it's actually not a function. So let's just not for now. We might later just to kind of see what's happening, but point out here. Eliminating the parameter t is not particularly nice here. It leads to some sticky situations. So let's just plot some points. So we're going to have t, and we're going to have x, and we're going to have y. So let's say t goes from -2 to 2. X is going to be, well, t squared is 4. Actually, 2 squared, -2 squared is 4, then 1, then 0, then 1, then 4. And if we get different y values out here, you're going to see that it's not a function, right? Because you're going to have, or it's not a function of x, because you're going to have one x input, 4 and 4, giving two different y outputs, which happens in parametric curves sometimes. So let's see. So plugging in -2, I get -2 cubed minus 3 times -2, which is -8 plus 6, which is -2. And then plugging in 1, I get 1 cubed minus 3 times 1, which is also -2. Okay. Plugging in 0, I get 0. Plugging in 1, I get 1 cubed minus 3, which is, I made a mistake here. And no fault of you for not catching it. I accidentally plugged in x equal to 1 when I was supposed to be plugging in t equal to -1. Sorry about that. So it's -1 cubed minus 3 times -1, which is -1 plus 3, which is +2. Down here, when I plug in t equal to 1, that's where I get 1 minus 3 being -2. When I plug in t equal to 2, I get 8 minus 6, which is +2. So let's see if we can graph this thing. So let's see. Again, I'm not actually plugging in the t values, I'm just thinking about them. So I'm going to have 0, 0 as a point, and 1, comma 2 as a point. And so is 1, comma -2. So clearly not a function of x. And then I'm going to have 2, comma 4 and -2, comma 4. Sorry. Don't look at this column, James. 4, comma -2 and 4, comma 2. Sorry about that. So 4, comma 2, 4, comma -2. And then this is going to be really important to actually label what t is in each spot so we can follow the correct path of travel. So over here at 4, comma -2 is when t is equal to -2. And then at 1, comma 2 is when t is equal to -1. And then 0, 0 is when t is equal to 0. 1, -2 is t equal to 1. And over here is t equal to 2. So we're going here, then there, then there, then there, then there. So it's going to look kind of like this. Let me be super smart for 1 second. Sure. Only 1 second, though. Just kidding. Oh, I want that to be, sorry, that should be right. Oh, yeah, okay. I always make that mistake. Okay. So I'll point out, even though we haven't set that yet, there is an intercept at 3, comma 0, which just trust me for now. So this is going to look kind of like this. It's a little straighter than I meant to look there. And it should be symmetric about the x-axis. And we're going this way. Cool. In fact, the way I found the x-intercepts is the way we usually find the x-intercepts. And actually, that brings up a better point. The way we find anything in these parametric curves, whether it's intercepts or derivatives or integrals, is usually kind of starting with the usual thing and then employing some trickery, to be really honest. And again, it's not really trickery, but it feels kind of like trickery. So x-intercepts, cool, set y equal to 0. So set t cubed minus 3t equal to 0. So t factors out, you have t squared minus 3. So you either get t equal to 0 or t equal to plus or minus root 3. And the mistake I always make when I start graphing this thing is I was like, well, cool, 0 is 1 intercept, and then I'm like, root 3 doesn't seem like the right place for the intercept to be because it's not. Because if t is root 3, x is then t squared, which is 3. So that's why we got 3 comma 0 as an intercept and 0 comma 0 as an intercept. But again, I always make that mistake. So how do we find the derivative here? I really want to find actually when the derivative is equal to 0. When or where, I don't know, whatever you want to say it. So how do we find dy dx here? Well, there's a trick people use where you just divide the top mod by dt. But that really is kind of a trick. It's actually coming from the chain rule. So let's take a look for just a second. So yeah, let's go. Then we'll leave some room here. So just off to the side here. Let's say we have y. Well, let's pretend like we could have found y equal to f of x. That relationship is out there somewhere. But we're given x is a function of t and y is a function of t. Right, those are the things we know. So I'm going to rewrite this as y is a function of t equal to f of x is a function of t. Now, what am I looking for? Well, I want dy dx, also known as f prime of x. And again, all this, I should have said, you don't have to or need to write this down. I'm just trying to give you some justification for why we're going to say the thing we're going to say. But again, if you want to, it's totally fine. Just, it's kind of my thoughts on paper here, which I guess is always the class, but okay. So anyway, I'm going to differentiate both sides of this. I'm going to use the chain rule. So on the left-hand side, the derivative of y of t is just y prime of t. But then the derivative of f of x of t is f prime of x of t times x prime of t. But y prime of t is just another way of writing dy dt. F prime of x of t, or just f prime of x, is my dy dx. And x prime of t is dx dt. And then if I isolate dy dx by dividing both sides by dx dt, I end up getting dy dt over dx dt is equal to dy dx. Which is a bit more of a justification for why we're actually allowed to do what we do. So it really, really, really is the case that dy dx is equal to dy dt over dx dt. It's kind of great. You see a few faces that look like you don't quite believe me, but you want to. It's okay. The nice thing about this is it looks like you would want it to look for the math to work out the nice way, right? You can think about, hell yeah, definitely, I can imagine those dt's canceling by flipping and multiplying and getting dy over dx. Cool, it works. I'm going to save this paper here for when we get to the second derivative stuff. So back to this, I'm going to find when / where dy dx equals 0 by first finding dy dx. So dy dx is equal to dy dt over dx dt, which is going to be dy dt is going to be 3t squared minus 3. And dx dt is going to be 2t. Bless you. And sometimes it pays to simplify this. Sometimes it doesn't. Sure. So if I want this to equal 0, though, I just want the top to be equal to 0. So I'm going to set 3t squared minus 3 equal to 0. And I'm going to end up getting t squared equal to 1 or t equal to plus or minus 1. Which we know is the point we've already plotted, right? It's right there and right there. So at t equals 1, which is the xy coordinate 1 comma negative 2. Yeah, I believe we have a horizontal tangent there. It certainly looks like it, right? And similarly, at t equals -1, which is the point 1 comma positive 2, yeah, up there we also have a horizontal tangent line. So it seems good. What if I wanted to find where I had a vertical tangent line? Well, horizontal tangent lines have a slope of 0. Or I should say horizontal lines. Doesn't matter if they're tangents to anything or not. Horizontal lines have a slope of 0. Vertical lines have what kind of slope? Yes, but I'm going to say something else. You're not wrong. Undefined, right? The vertical line is the only type of line whose slope is undefined. Any other slope, any other line has a slope that's a real number. So essentially, I'm saying, where is my derivative undefined? In other words, if I look at my expression for my derivative, I want the denominator to be 0. So 2t equals 0 means t equals 0, and my coordinate is 0, comma 0. And yeah, I'm not even going to draw anything else. It certainly looks like the tangent line right there is the y-axis, a vertical line. Cool. All right. So what about, that's an interesting question I hadn't considered before. Hmm. Hmm. Interesting. Sorry, I was just having thoughts. I was asking myself, where is the thing increasing or decreasing? Which is something we don't really think about parametrically, but I think it still works, right? Because if x is bigger, if t is bigger than 1, the top is positive, the bottom is positive, and if t is bigger than 1, it's certainly increasing. If t is between 0 and 1, the top is negative, the bottom is positive, so it's decreasing. If x is between -1 and 0, is it decreasing or increasing? Well, let's see. The top is negative, the bottom is negative, so it's increased. That's weird. This part we say is increasing, which I guess looks right, but feels weird because we're going that way. But I guess we don't care about the direction of travel, we just care about the shape of the graph. And technically, so I feel like increasing is not the right word there. Has a positive slope of a tangent line is a better way to say that. So it's probably inappropriate to talk about increasing or decreasing this for parameterized functions because we've got kind of different directions of travel.
Increasing and.
I think we would say we don't say anything is the better answer.
1, 2, 3.
From 1 to 3.
Like x equals x.
But which point on the curve? From this x equals 1 to x equals 3, or from this x equals 1 to x equals 3? Right, which means I think we have to talk because really this isn't a function. So I think that's one of the actual problems here is this isn't a function of x actually because it fails the vertical line test. So we can't really talk about increasing or decreasing this at all. So I rescind the question. I think it's a bad idea. All right. How about concavity? It's not that bad, except it's kind of that bad because we have to find the second derivative. So here's the trick for the second derivative. So just like before, we said dy dx is really dy dt over dx dt. Or what you really think of is this is the derivative with respect to x of some function y. So now all we're going to do is we're going to replace y with the derivative of y. So we're going to say the derivative of y prime. Well, that's going to be the derivative of y prime dt over dx dt. Or if you prefer, you can write it as, I don't really want to write it that way. But then to be more explicit here, this is going to be d dt of my y prime over dx dt. But then that's really, well, y prime is this jazz here. So it's really d dt of the dy dx we already found over still just dx dt. It's a little bit weird. And then, of course, I should write it as d squared y dx squared. But that's the idea. You're just kind of replacing y with the y prime and then acting on it the same sort of way. And I was going to write this on my other piece of paper, but I totally didn't. It's like, do I want to use a changeable thing? No, not really. Okay, so let's find the second derivative, and then we'll talk about whether it's concave up or concave down. And it is going to look right, which is great, because it'd be terrible if it didn't. So find d squared y dx squared. It's going to be d dt of our dy dx from before, and dy dx from before was 3t squared minus 3 over 2t. And on the bottom, it's just going to be whatever dx dt is, which is going to end up being our 2t again. So the bottom doesn't get more complicated than it was before. It's still the same 2t on the bottom. Now, I should be doing myself a favor here. I shouldn't use the quotient rule on the top there. I can certainly divide each of those terms by 2t. So let's rewrite this as d dt of 3 over 2t minus 3 over 2t. I know it sounds like I said the same thing, but one of those t is on top and one of those t is on the bottom. Right? That's definitely a better way of doing it over the derivative of x, which is t squared. And I really should have probably written this as 3 over 2 times t to the negative 1 to make my life better. So then we differentiate. We get 3 halves minus the derivative of 3 over 2 times t to the negative 1 is minus 3 over 2 t to the negative second, all divided by 2t. Let's simplify this a bit. So simplifying here, I'm going to factor out the 3 halves on top. I'm left with a 1 plus t to the negative second, or I'm going to write it as 1 over t squared over 2t. So if you set this equal to 0, not that we need to, but I'll just point out this is never equal to 0. Because the numerator is never equal to 0. 1 plus 1 over t squared can't ever equal 0. What does that mean? It means there's no points of inflection. There's no point where we change from, no, I'm just saying there's no points of inflection. So that means the second derivative here is either always positive, no, is either positive or negative, right? But it's never 0. It could be undefined when t equals 0, which I guess makes sense because if we look back at our graph, at t equals 0, there's not really concavity, right? It's like opening rightward, which is not, when we're talking about concavity, it's concave up or concave down. Another way to say that, which we said before, I think, is a function's concave down if its tangent line lies above the curve, and its concave up if its tangent line lies below the curve. So right here, the tangent line being off to the side doesn't meet either of those definitions. So there isn't really any concavity to speak of at t equals 0. Now, it sure looks like this thing is concave down when t is negative and concave up when t is positive. Let's see if that's true. So my second derivative, d squared y dx squared equal to this 3 halves 1 plus 1 over t squared over 2t. Well, clearly the top is always positive because it's 3 halves times 1 plus 1 over t squared. And the bottom is going to fully determine the sign. So this is going to be positive if t is positive. And it's going to be negative if t is negative. So yeah, this curve is concave up when t is greater than 0, concave down when t is less than 0. Interesting. Okay, what time is it? 4:07? All right. Sure. So then I think, well, not then. Um, is this example good for that? Sure. Yeah. So I'm just trying to think about how good this example is for the other things. So then there's like four other things Babson mentioned about these parametric curves. So he talked about, or he briefly mentioned kind of how you could talk about area. So for example, well, if I want to find the area, and again, we might look at this example. Yeah, I'm feeling relatively confident. We'll see how it goes. So I'm gonna look at this section right here, where that was, let me grab just that point. So this is right up here is t equal to -1. Over here is t equal to 0. Over here was t equal to -√3. Yeah. Okay. And this point was x is 3 comma 0. Sorry, xy is 3, 0. This is 1 comma 2. This is 0 comma 0. So normally you'd find area by just doing the integral from, a to b of your y dx, or whatever y is as a function of x. But then this is where we do the cheater thing. We're like, well, really, if we turn it to being in terms of t, it's y of t. And instead of writing dx, I'm going to write dx dt times dt. So then it becomes the integral of the parameterization of y times the derivative of the parameterization of x dt with the appropriate t limits of integration. Kind of cool, I think. So if I want to find this area here, which again, I'm feeling pretty dicey about, to be perfectly honest, but we'll give it our best shot. It should be the integral of our y of t, which was t cubed minus 3t, times our derivative of x. So maybe I should write them over here. Y of t was t cubed minus 3t. X of t was t squared. So the derivative of that's going to be 2t times dt. Now here's an interesting question. And I do think it's interesting. Are we integrating from t equals -√3 to t equals 0? Or from t equals 0 to t equals -√3? I think, and I'm not sure, so we're going to check to see. I believe you have to go from left to right, meaning if you need t to be out of order, that's okay. The order needs to be from left to right. So I believe it should be 0 as the lower limit and -√3 is the upper limit. Let's hope it's right. Okay, so let's do the integral. Let's multiply it out first. Come on, James. So integral from -0 to -√3, multiplying the 2t through, we're going to get 2t to the fourth minus 6t squared dt. These numbers are not going to be super nice at the end of the day. Oh well. And then, we could do that. Be smart. Sure, fine. So then integrating this, we get 2t to the fifth over 5 minus 6t cubed over 3, which is 2t cubed from 0 to -√3. This is where I wish I picked different numbers. So that's going to be, sure. All right, so what's -√3 to the fifth? Well, it's -√3 times -√3 to the fourth. And the square root of 3 to the fourth power is 9. It's the square root of 3 squared times the square root of 3 squared, which is 3 times 3, which is 9. And over here, minus, again, I'm going to have a -√3, and then I'm going to have a 2 times the square root of 3 squared, which is going to be a 3. And yes, I'm ignoring the negative because I'm squaring it, so it's not a big deal. Minus 0 minus 0. And now the hope here is that the thing I've written down is positive. Let's see if it is. So I'm going to have negative 18 over 5 times √3 plus 6 √3. And thank goodness 6 is bigger than 18 over 5. So this is equal to root 3 times negative 18 over 5 plus 6, which is 30 over 5. So I end up getting 12 root 3 over 5. What a beautiful number. I kid. But it works. This actually gives us the area under the curve. So when you're doing this, if you are actually trying to find the area under a curve of a parameterized curve, you do have to integrate. Sorry about that, everybody. I don't know why I cut out there, but now we're back in business. Okay, so oh my gosh, maybe if I can get things sorted here. All right. So I don't think we really need to do examples for the rest because it gets really kind of numerically tedious. But I'll just point out the other ideas are the same kinds of things. So just like before, when you were finding, say, like a volume of revolution, if I had something like, you know, this sort of thing, and I was revolving around the x-axis, typically I would say, well, my volume is equal to the integral of pi times my radius squared, which is my function squared, which is my y squared, right? This is y equal to f of x times dx. And then we do the same trick we just did. We say that y is really y of t. And dx is really dx dt, or x prime of t times dt, from t equals whatever to t equals whatever. So that's how you can find the volume of revolution using parametric equations. And you can do the same sort of thing for arc length and surface area. Arc length and surface area, I think, are even a little bit trickier, though. Yeah, because well, arc length isn't too bad. For arc length, we would typically find the length as the integral of ds. And we even talked about how ds really was actually defined parametrically in the first place. How it's the square root of dx dt squared plus dy dt squared dt. So that's kind of actually not terrible at all. And then good old surface area. Although someone showed me the surface area problem from your guys' midterm. That problem was weird with the surface area of the outside and the inside stuff. I see some upset faces at even mentioning it. But yeah, I was like, that seems like a really so what I think happened honestly is you all did really well on the first exam, like the mean was like 80 or something, and your teacher said I have to make the next one harder to spread people out. And I looked, and the average of the second one was like 56 out of 110 or 112, where it's like basically like 50%. So yeah. I understand why someone would do that. I don't know if I necessarily agree with doing that, but that's probably why your second exam was so much harder, was because he was trying to get some separation in the grades. Anyway, for surface area, so again, it's the usual idea of being equal to 2 pi times your radius times your ds. And if we're thinking about going around the x-axis, so this is really surface area around the x-axis, well, then our radius is y, because it's how high we are, right? You're thinking, instead of taking the volume here, you're thinking of taking this and taking that little bit right there and revolving it around to get your rubber band shape. And the area of the rubber band is 2 pi times your radius times your ds, but your radius is y of t. So it's 2 pi times the integral of y of t, and your ds hasn't changed from the previous problem. Your ds is still the square root of dx dt squared plus dy dt squared dt. If you were going around the y-axis, your radius would be x of t. So surface area x-axis is like this. Surface area around the y-axis is 2 pi integral of x of t times still the same ds. Mm. And I will, instead of torturing you with these examples, I'll say you should look at these examples on Grant's webpage because they are kind of neat, but they're really a giant pain for everyone to watch me work out in front of you. So I'm going to say, let's call it early on a Thursday before a 3-day weekend. I know you all have class tomorrow, but you don't have to go. I mean, you can do whatever you want, right? So obviously no class on Monday because that's the holiday. And I'll see you all on Tuesday before your exam on Wednesday. And you should come on Tuesday with questions. Yeah. Has he posted any kind of practice exam? All right. I will see if I can find something to post. I will fully admit I've got a lot of things to do before tomorrow, so I might not find anything. But I will see what I can find. I should have something relatively ready to go. Have a lovely 3-day weekend.